In the last video, I've talked about how the voltage induced in this setup depends on the flux, the magnetic flux that goes through this area, and that's given by this quantity B times A here. So the B times A here is actually the flux, which I called phi. Now, one important thing to note is that when this magnet is moved away, the phi drops to 0. Okay, so the important thing to note here is that it is this change in the flux that induced the voltage. Okay, so I'm going to add the word change down here to remind ourselves. And just having this flux there, just having the flux going through this loop on its own, that does not cause any voltage. Right? If I don't move the magnet, it doesn't matter how much flux I have, there's no voltage. It's only when I move the magnet away, when the flux drops to 0, right? It's only when there is this change that I get a voltage. Right? So flux change is the word, is the important word. Okay. What I want to look at now is how this induced voltage would also depend on the time. Let me clear this away. Suppose this time that I keep the same magnet and I keep the same loop, so that my starting flux, my starting magnetic flux is 0.1. Instead, I'm going to try and change the time it takes for me to whip this magnet away. Okay, so I already moved the magnet away quite fast in the last video, as fast as 0.01 of a second. Right? This is the time that it takes me to move this magnet to a place far away where its field cannot really reach this loop anymore. So imagine now that I do it even more quickly. Suppose I whip it away even more quickly in 0.001 of a second. Okay. Then what I'll find, if I can actually read this voltmeter just as quickly, is that the voltage would be about 0.01. In other words, if I whip it away in a time that is 10 times shorter, meaning that I whip it away 10 times faster, then the induced voltage will be 10 times bigger. And if I can somehow do that even more quickly in 0.001 second, right, let's say I'm really fast, I'll find that the induced voltage is 0.1 volt. It will increase by another 10 times. So it looks like the induced voltage is also proportional to the speed with which this flux is changed. Right? Because the faster I move this away, the faster the flux will drop to 0. So this rate, I can call this the rate of change of the flux, okay, which I can think of as, for example, as say the flux change over the time. This rate of change of the flux, I can think of this as being directly proportional to the voltage V. Okay, these two are directly proportional in the sense that if I change the flux 10 times faster by moving the magnet away 10 times more quickly, then the voltage would increase by 10 times in that sense. Now this is an important observation. We now have a fairly complete picture in that we know how the voltage induced depends on the flux and the time. And the flux, we know, in turn depends on the area of the loop and B, magnetic flux density, which is related to how strong the magnetic field is. So we have an important relation here. Okay, and let me write this down. In a more tidy way. The induced voltage is equal to the rate of change of magnetic flux. Okay. If I put this in symbols, induced voltage is V. I'll call that V. I can think of this as the change of flux over the time taken. Change of flux over the time taken. Now you might sometimes see this as written as V equals to d phi by dt. So if you've learned calculus in mathematics, d by dt means the same as the rate of change. Okay, and you would also see a minus sign if you look at textbooks of these equations. You would also see a minus sign added in front of that. Now I'm going to explain the minus sign in a later video. Okay. Now, for now, I'm going to just write down the name for this relation. There's a name for this relation. It is called Faraday's law of electromagnetic induction. Electromagnetic induction. Okay. Now the main ideas about this law is contained here. However, there are a few more details about this law that I'm going to talk about next. One of them is the minus sign there. The minus sign, right? Maybe we can think of the minus sign as the subject of another law called Lenz's law that I'll come on to later. For now, there are two other details. Yes, there are two other details in this law that I should mention. One is the idea of flux linkage, magnetic flux linkage. The other is what happens if we have a non-uniform field. Now previously, in the last video and up to now actually, I have emphasized that I assume in this thought experiment that I did, I assumed that the magnetic field is roughly uniform over this area. It is roughly, magnetic flux density is roughly 0.1 Tesla over this volume and in the same direction. But what if it's not? What if it is not? If it's not, then what is phi? Okay, so there is this issue that I need to talk about a bit, and then there's this thing about the flux linkage. So let me start on this.